So good afternoon. My name is Stephen Lythe. I'm the CEO of CANY and just here to facilitate today's conversation on Local Law 97 and how to comply by 2024. I think it's worth saying that I'm sure we all appreciate that the scrutiny on the building stock of New York continues to develop increasingly. And as we see buildings that are obviously aging, FISP is now asking more and more questions of the condition and safety of our buildings. Alongside that, we have Local Law 97, which presents some very specific and challenging standards with respect to the energy performance of the building. And in thinking this through, CANY has fostered a partnership, particularly with MGEngineering, to look at these two problems and recognize that there is huge value in considering them together. By developing an end-to-end view of what is going on and an integrated approach to understanding both the interaction between FISP and Local Law 97 and how to address the resulting challenges that need resolution. So today's focus of the webinar will take us through both the timelines, what is included in the Local Law 97 investigation, how we look at FISP, and how we bring those two together through a case study and understanding what it means from an ownership perspective, and then the next steps. I'd like to introduce the panel, John Rudisill, Thomas Seminara, and Adam Farber. And perhaps, John, you could just introduce yourself to the audience. Thank you.
Good afternoon. I'm John Rudisill, and I'm a Senior Vice President with CANY. I've been working with CANY for a little over 22 years. My primary focus these days is with ground-up new construction, redevelopment of existing buildings, which includes, in some cases, facade replacement, facade recladding, with a heavy emphasis on energy performance upgrades. We deal with a lot of energy analysis and modeling with the building enclosure systems. And next is my colleague, Thomas Seminara.
Good afternoon. Likewise, John and I have been working together for the past 22 years here. I'm a Senior Vice President at CANY as well. My focus primarily revolves around existing buildings, FISP, formerly Local Law 11, and managing the programs that deal with repair of those buildings.
And Adam.
Hey everyone, Adam Farber here. I work for MGEngineering. MGEngineering is a full service mechanical, electrical, plumbing, fire protection engineering firm. We've got offices in the city and on Long Island and in Miami. We focus on ground up residential as well as building retrofits, gut renos, rehabs, etc. I run the energy and sustainability department at MGE, so we focus on all things energy related, including some building inspections, building energy studies, and of course Local Law 97 compliance, which we'll get into more through the webinar.
Great.
Next slide here.
Yeah, so this is, as Stephen indicated earlier, there are two major challenges that we are building owners face, and the FISP has been around for a very long time, and we are currently in the FISP 9 cycle, which the graph on the right-hand side illustrates how FISP aligns with Local Law 97. Our current cycle of FISP gives building owners until approximately February of 2024 to comply with making their buildings facade safe and stable from a public safety perspective. Local Law 97 was enacted in 2019, and that first cycle comes into full effect at the end of the current FISP cycle. So in 2024, building owners will be utilizing their energy usage data to file the first report in 2025. Now, what that means, and maybe Adam, you can touch upon this a little bit more. Building owners are going to submit a report indicating what their current energy usage is, and that translates to a certain amount of carbon emissions, and we have limits established. So what does it mean if a building owner is over those allowable carbon emissions in 2024?
Yeah, I think most people already understand the basics of Local Law 97, but the very short story is that the law puts a cap on how much energy your building can use. So if your building uses, and the cap is going to be based on the building type, if it's a residential building, a commercial building, a retail structure, et cetera, and the size of the building. Obviously, larger buildings will have a larger energy allowance. So if your building is given a cap of a certain amount of energy, and there's a straight formula that determines that, which we'll go through later in the webinar, and your building exceeds that cap, then you are liable to pay a fine. The fines can be hefty, which again, we'll go through later. But the one real important point, which we're going to touch on in this, in the course of this webinar, is that the cap that your building has drops progressively over the next 30 or so years. The first cap is established for the year of 2024, the year of energy usage, which will be reported in May of 2025. And then those caps drop again every 5 years. So in 2029, 2030, the cap drops significantly. And if you use the same amount of energy that you had been using the year before, you may not have had to pay a fine before, but now you have to, you will be in the liable amount. So we'll get into the specific numbers, as I said, later on, but that's something to recognize, is that the building department is giving us really about 10 years to hit the 2030 limits, and to really get your building in gear. And those 10 years, and this is a key driving point that we're going to get to, should be used to develop a comprehensive plan for your building that will address the Local Law 97 considerations and the Local Law 11 FISP considerations. And to that end, John will discuss more.
Yeah, I mean,
actually, Adam, before John moves on, I had a great question come in, and I think it's just helpful to clarify. Paul is asking online, my building's configured more like a campus where we have 8 interconnected buildings on a single block. Do we need to submit data for Local Law 97 per building over the 25,000 square feet, or is there an option to submit as a complex? Our power distribution is intertwined throughout all the buildings in the complex.
So the letter of the law allows, I think, 2 buildings together, but it also allows for unique situations. I think we should, the fact that the power distribution is intertwined is a real great argument to me to combine the buildings. Your overall cap will be very high, obviously, but your overall energy usage is going to be very high as well. And so that's something that we can address on a specific level. It is a good question, Stephen. Thank you.
And I would just encourage anybody, if you have questions, please use the chat or the Q&A function, and we'll make sure we address them as we go through the presentation today. Thanks, Adam.
Great. So let's talk about the process on the next slide here. So there's a reason why we're looking at both the mechanical systems and the building envelope together. I mean, clearly, the inefficient mechanical equipment is going to increase cost of operation, but we also need to understand what is driving those costs. Building envelopes have a huge impact on that, and we'll talk about that a little bit more. But you know, the FISP 9 and 10 FISP is looking at public safety. They're looking at damaged veneers. They're watching out for things falling off the building. Building owners are going to have to, for a lot of these buildings that we're going to look at, do major construction projects that, again, make the facade safe, but may have no impact whatsoever on air infiltration, on how the building envelope performs, and that drives energy costs. So our process, our combined comprehensive process, involves building envelope inspections, testing. We'll analyze the building envelope in terms of thermal performance and provide that data to someone like Adam, who will then incorporate that into a model. You're going to be doing a top-down review of the mechanical systems and their operation, and determining what the overall costs are and what's driving those costs.
Also, as part of the inspection, as it relates to FISP, we'll be doing up-close inspections. Typically at CANY, we We love to use IRA, industrial rope access, as a means of inspecting buildings for the flexibility it offers us and the comprehensive evaluation that we're able to perform via the multiple drops. Also, we would recommend some probes being done. And the probes will facilitate the intimate knowledge of the backup wall, the facade, the integration of the windows, and how the components that were actually built, maybe not per the drawings, as we often see, actually are existing in real time. And those physical elements get inputted into the thermal modeling to get a really highly accurate evaluation of the structure.
So let's talk about a building that we're actually in the midst of this investigation. We actually completed the investigation. So let's talk about that in a little bit more detail. Obviously, for owner confidentiality, we can't show photographs of the actual building, but we're going to show the photographs and conditions of similar buildings and similar types of construction. So the building that we're actually investigated is, it's a very large Upper East Side residential tower. It's an apartment building that was built in the circa 1990. It incorporated, much like you see in this photograph right here, projected balconies, areas of significant glass and glazing, brick masonry that is supported both by concrete eyebrows as well as
Continuous shelf angles.
Yep, shelf angles. So this is a building that CANY got onto the ropes and went outside and did a hands-on inspection of all 4 sides or 6 sides of this building, and really did a deep dive into what the FISP conditions were. And that's when we discovered that the owner had significant exposure. They are executing a major project just to render the building safe in terms of remediating damages. And we'll show some pictures of what those typical types of damage are. But on a parallel path, Adam did what I guess you would call now as an enhanced level 1 ASHRAE investigation. Maybe you can touch upon what that involves.
Yeah. So what we looked at, John and Tom are talking about the envelope analysis that they're doing, and once you're looking in detail at the envelope analysis, you really have to use that opportunity to also look at the energy performance of the envelope. In terms of local law 97, which again relates solely to the energy output of the building and the energy use of the building. So we looked at the air infiltration and the window thermal performance of the building. Those play an enormous role in the operation of the mechanical systems.
Right, to that point, we actually engaged a contractor to perform probes to actually remove sections of the brick masonry on the outside and take a look at what's back there. And what we found, these brick masonry veneer buildings did not, even in the 1990s, did not incorporate air moisture barriers on the backup wall
Or insulation.
And another key thing is that we actually we tested the window assemblies. We didn't want to make assumptions of how the windows were performing. These are 30-year-old horizontal sliders and window wall. We actually got out there with a testing agency, Building Envelope Testing LLC, did some air infiltration testing for us, as well as analyzed the existing frames and the glass and glazing to determine the U values, which you needed for your model for accuracy, and solar heat gain coefficients, how much load the building envelope is imposing on the mechanical systems.
In this building too, we had some leakage conditions that we were dealing with. So we had the luxury of also doing some probes on the interior side in some isolated areas.
Water infiltration.
Yeah, looking at water infiltration. But that also gave us another vantage point to see the conditions of the backup wall and the typical poor construction of buildings built of this type in this era that we often see. But again, we had the luxury of doing some interior probes. Probably wouldn't do that on every, in every scenario, but this worked out really well, and it was give us the ability to really verify and confirm our results, both in modeling and in actual testing.
Well, it gave us that data, and you could say that tested this, that not only did it give you the accurate data of what how the mechanical systems were used and why, but what the cost of the LL97 exposure to penalties would be.
Right, absolutely, which we'll get into specifically later on.
So let's look at briefly a couple of other building types that are similar to our case study here. So on the next slide, we'll have a couple of photographs of Yeah.
Yeah, so the building on the left, it's an older building out in Coney Island, built in the 60s, cavity wall construction, continuous shelf angles, brick masonry. We've done a tremendous amount of work in the past on these buildings. And again, all our suspicions are continuously confirmed when we're looking at these cavity wall buildings. Insofar as shelf angle issues, poorly constructed backup wall with large voids that lend itself to tremendous air infiltration. The picture on the right is a building built in the early 2000s with a little bit more modern take on the construction that we see often now with exposed eyebrows, continuous concrete floor slabs that come out to the edge of the building that provide support for masonry. Nonetheless, backup wall conditions still exist in the same poorly executed and detailed fashion.
But the thing is that none of these, even aside from, yes, the poorly executed, but the real fact that drives home this is that a building constructed in 1960 up until the 2000s essentially had the same wall composition: brick masonry veneer, airspace, backup wall, and then interior finishes.
Right.
No air moisture barrier, no insulation. So a building from the 1960s, that envelope could be performing just as well or poorly, so to speak, from an energy perspective, as a building that was built in 2001.
Right.
It wasn't until the early 2000s with the the New York
code change
required continuous insulation and air moisture barrier. So you've got huge exposure to the building stock of this era.
One benefit to the little bit newer buildings is that typically 60s, 70s, 80s flashing systems were PVC, and the PVC product they used on the shelf angles was, as you'll see a little later on, is a really poor product and lends itself to
really contributed to major FISP problems.
Yes.
The materials that were used up until the 90s was a driving factor here. It deteriorated, it degraded within the wall cavity. The next slide shows another comparison. The building on the right-hand side was the late 1990s construction, huge residential tower. And the building that you see on the right-hand side is very common in New York City. The white glazed brick, that was a 1960s era building, white glazed brick, air cavity, backup wall. The thing in this photograph that we're illustrating is that a lot of those buildings they performed window replacements. It was quite ubiquitous in the 80s and the 90s, but those 35-year-old windows were very early technology, thermal break, not that great. The glass did not have the kind of low E energy enhanced coatings that we have today.
If they're insulated glass units at all. Very often they're single glazed, non-insulated units.
And what you see there is also the double hung windows, and the double hungs and the horizontal sliding windows are, as compared to today's technology, terrible in terms of air infiltration and performance. I mean, when they came out of the factory, it was mediocre and not being maintained for 30 years, or maybe not being properly cleaned or doing the routine maintenance. They're performing 4 times worse than they were 40 years ago. So that's a huge driver. That's what's really driving the heating and cooling costs of these buildings. That's a major, major problem. But we're going to show a couple of pictures of the typical FISP conditions that we have to deal with. So in the next slide.
So again, the overview shows slider windows, continuous shelf angle supporting masonry at the fenestration, but also projected concrete balconies. All those elements are constant FISP local law 11 maintenance items that are reoccurring on these buildings. The close-up photo shows the underside of a typical parapet that you would see supported by shelf angles. In that photo, you can see some minor corrosion. Doesn't look too bad on the surface, but this is just a precursor to leakage and long-term facade repairs. As you see in the next slide, the conditions when left unattended to get a little worse. Here is a probe photo we took that shows the backup wall, the cast in place concrete structure, and the window.
And the CMU block and the window jamb, right?
So between the CMU block and the window jamb, there's a 3/4 inch void there that goes straight to the backside of the drywall and the interior finishes.
A key takeaway here is that you're looking at a picture. Once you take out the masonry veneer, and what you see behind it are there's no insulation, there's no waterproofing. there's huge gaps between, on the left-hand portion of that is cast in place concrete structure. And then you see CMU block as a backup wall. Then you see air, and that all that is wide open to the backside of the drywall on the interior of the apartment. And so, Adam, you can, this is, mechanical guys love to see this stuff here, because this is what's driving the operating cost of the equipment here. You have no insulation and no air barrier.
Yeah, I'd love to see it as something that I get hired to fix. I hate to see it actually in real life in the field.
Right.
But John you're absolutely correct that this itself is going to raise the heating and cooling load on the building tremendously. And so, having nothing to do with the mechanical systems themselves, you will place a real strain on the systems. In other words, the units you install, the mechanical systems could be the most efficient in the world, and the building will not operate efficiently because you've got these huge air leakage gaps. And again, that really drives us home to the main point that we're getting at here, which is this combined approach of looking at local laws 11 and 97. And when you take them together, you can address the safety elements which John and Tom have been addressing, and the mechanical energy elements, which is more my wheelhouse.
The photograph on the right shows, again, what Thomas was talking about earlier. You're looking up at the bottom of a shelf angle that's supporting brick masonry. You see the corrosion there.
And you can see the buildup of a little bit of rust right where the brick and the shelf angle meet at the bottom of that photograph. This is at this point, it's not a big deal. It's not causing any damage to the brick
yet.
Yet, right? But this is, once it starts, it spreads, and it is extremely problematic. And if you look at the next slide here, you'll see the advanced corrosion and problems that do eventually occur.
Well, the steel that's embedded in the masonry wall, look, if we're looking at a building on cycle 9 and we don't see any damage to the masonry, we don't see any outside visible corrosion, you can pretty much be guaranteed that it is happening in the building. And if you don't have a problem in FISP cycle 9, you will have a problem more than likely 5 years down the road, because in these photographs, like you see, once that steel, the embedded structural support for these masonry veneer walls starts to corrode and expands, then you've got yourself a FISP problem. And that's why building owners it's a serious challenge. It's a real challenge, because you've got to deal with this every 5 years. And of course, putting up a sidewalk bridge and mobilizing contractors and executing work every 5 years is extremely expensive. And you can do that and maintain your facades and fix your facades. But unless you get back there and deal with the actual thermal and air infiltration performance, you're not doing anything in terms of energy. And that's why your exposure to local law 97 penalties is huge. So we'll talk about a couple mechanical systems on the next slide here.
Yeah, so this is getting back to our sample building that we've been talking about. These are a couple of the mechanical issues, because we've been talking about the facade the whole time, and the facade is crucial. I just responding to a comment that someone posted a moment ago, that the air leakage on one of CANY's projects was 20 times. The air leakage on an existing building was found to be 20 times the acceptable rate for a modern construction. And that really itself illustrates the value of a well-maintained facade to the mechanical systems. Because again, the mechanical systems could be the most efficient in the world, but if you're trying to overcome just enormous air leakage, right? In the winter and the summer, then there's no way your mechanical system can compensate and maintain its efficiency and its low energy output. And that's with the most efficient mechanical system in the world. This building that we've been talking about, and most existing buildings and many existing buildings that we have, aren't the most efficient in the world. And I'll point out just a couple of the building and residential systems, the common house systems in this building. If you look at, starting from the right, these are original building chillers. I believe these are from the 90s. So they're not they're not super duper ancient. They're not terribly old. You can see that they're mid-repair, but they're not really, they don't have the efficiency and the capabilities that modern chillers have. The middle photo shows the cooling tower up on the roof. You can see that the water insulation, the water piping insulation, excuse me, is cracking. You can see that valve right in the middle of the photo. That's just a manual on-off valve. There's not any modulating capability, and there's certainly no automatic capability. And you can see the big on-off button off to the right. So there's no variable control for this. There's no variable speed for the motor or for the fans on this cooling tower. And that lack of controls capabilities in older buildings is a real energy use driver, and frankly, a very easy way to upgrade the energy use of the building. If you go over to the left-hand photo, which is the residential air conditioning unit, this is obviously going to be a tougher one to address because it's inside an apartment. But I just kind of want to point out at the very top of the photo, that is the extent of the controls that the resident has. So a person living in this apartment has one button that says fan speed and one button that says warmer or colder, and that's it. And residents nowadays, and this is something that I think Tom is going to touch on later, is the marketability, the overall marketability of the building when you look at the facade. But there are real marketability issues with older mechanical systems as well, because modern buyers are looking for more sophisticated systems than this. And they're looking for a system that they can control and maintain with web access over their phones, and frankly, have a much more efficient and controllable system. And something that just says colder and warmer ain't going to cut it for a lot of people, and certainly will not cut it for the energy use.
And it cuts their cost.
Absolutely. And it cuts the air costs, and it cuts the building owner's costs tremendously.
By the way, if you're living in a building and walk in the lobby and you see a D in terms of energy performance, that's not particularly appealing. So
absolutely.
People want to live in an energy efficient, environmentally responsible building with a great ACE rating. So let's look at the stats on the case study that we've performed here. So this is the result of the local 97 analysis that the calculations and the model that Adam, you performed with we gave all the building envelope thermal performance, how it was doing, real air infiltration, real U values, and real solar heat gain coefficients. And you can see that it defines, if they did nothing, you could execute all the FISP repairs, you have to, but if you did nothing in terms of the enhancing the upgrading the envelope and dealing with the mechanical systems, you've got $257,000 fines in 2024.
Just let's explain a little bit what the highlights mean, right? So 2024 building total, your first highlighted area, right, is the limit of carbon dioxide emission.
So I'll talk through this very briefly. So in this building, we've got, it's a residential structure. It's got a ground floor supermarket. And Local 097 does divvy up the usage of different building types, right? So the residential has a different limit than the supermarket has, which is why I split them out here. That's just to illustrate that the analysis isn't really, it's not a month-long analysis necessarily to find out how your building will perform, but it's not a 2-minute analysis either. There's a little bit of depth that is required. So the energy, natural gas, and steam usage, those are going to be the top 3 rows on the right-hand side. Those are provided straight from the building's current billing, right? This is a master metered building for electricity, so we have the total energy usage. Natural gas and steam are always going to be master metered, so or essentially always. So we have those numbers. We also have the natural gas in the supermarket did have a separate natural gas meter, although it had no steam usage. So we have the total amounts, and based on the building size and the allowances for residential and supermarket spaces, this building in 2024 would have a limit of about 2,700 tons of carbon dioxide emissions. The building's current carbon dioxide emissions is 3,600 metric tons. So as you can see, there are about 1,000 tons over the limit. That's an annual limit. And at 1,000 tons or 960 tons to be exact, the penalty is $268 per metric ton. And the building will therefore have to pay $257,000 annually starting in 2025 for the next 5 years. That is an annual fine, and that's based on the building's current usage, assuming that the building makes no upgrades to the mechanical systems or the envelope or anything else, lighting, etc. That is their annual fine in 24. I mentioned earlier that the building limits drop every 5 years. So their limited starting in 24 is 2,600 metric tons a year. In 2030, it drops to 1,544 metric tons a year. Their usage, again, they've made no upgrades in this building, so their usage would be assumed to be about the same. And that means their fine nearly doubles to $560,000 a year. So if this building does no work at all over the next 10 to 15 years, they would have to pay close to $3 million in fines, if my minute math is correct, which is why we are, we're looking at making upgrades to this building. And if you go to the next slide, what you'll see is, because we wanted to isolate the envelope and the envelope performance to this building. So I just took the bottom half of the chart. I didn't feel the need to reproduce the residential and supermarket breakdown once that was understood. But if this building just makes upgrades to the envelope. Now, upgrades to the envelope.
The upgrades to the envelope that we're talking about here is actually just simply window replacement.
Well, because they were faced with, you mentioned the energy fines accumulate to approximately $3 million. The exposure for FISP this cycle was a little over $3 million. All
right, and that was addressing building deficiencies and very minor leakage.
So what we determined is, we were working with Adam and say, well, look, even if you did some minor mechanical system adjustments now, it wouldn't mitigate the fines in 2024. But what if we replace those horribly performing 35-year-old windows? And then we modeled that. And what we determined, if you replace the windows, because you're already going to be outside the building, hanging scaffolds, a sidewalk bridge, executing a major facade repair project. While you're at it, you replace the windows, and that would eliminate, number one, your building would be rendered safe from a FISP perspective, and you'd have huge energy efficiency upgrades that would eliminate 2024 local 97 penalties, and as you can see, would actually result in a reduction of the 2030 penalties.
Right. So, and again, this is just the window upgrade. So we haven't spoken really about air sealing through the opaque facade. We haven't spoken about any mechanical upgrades. And so what this does is this allows the building 10 years, or at this point, I guess, close to 8-9 years, because we've eliminated the 2024 penalty, right? And the reason is that the building's annual usage, which is currently about 3,600 metric tons of carbon dioxide, their annual emissions, I should say, we project that to drop to under 2,000 metric tons, which is an enormous drop and gets them considerably under the 2024 penalty. And that will allow the building time to get their affairs in order to look at mechanical upgrades that they would need to make. And the envelope combined with mechanical upgrades should be sufficient to get them under the 2030 penalty amount as well.
Right. This is a time when it buys them time to, number one, you don't have any fines, you're stay compliant with FISP, and it gives us time to investigate and develop a long-term plan of action for compliance. And that's what Local 97 is all about.
Right. And also the long-term plan, and the reason, the main reason we see this Local 97 and FISP integration is that we would put together a facade reclad program that would take them into 2030, 2040, time to budget out, time to save the money, do the assessments, apply for some PACE financing, do whatever it takes to get them to the point that in 15 years from now, 20 years from now, they don't have to come back and spend $5 million every 5 years, $6 million every 5 years to repair an aging facade that is continuously burdensome.
In this case, we've got a 35-year-old facade. The owner right now is executing, like you said, what we're going to call our phase 1 program here. We're looking at what phase 2 will be, which would be inactive before 2030, which Adam,
Right.
I think that includes the replacement of the chillers, right? On this building, hot water heaters, installing some automated controls. And we can do that in a phased approach so that when we get to 2030, we're in a good place with local 187. And we're looking at you're looking at other major mechanical system upgrades that would be implemented beyond 2030.
Right.
But to Thomas's point, we still have this masonry veneer.
Right.
That no matter what you do, it would always continue to deteriorate over time. It's a cycle, exposed steel, embedded steel, exposed concrete. It's all subject to the weather elements. So now we're looking at what can we do to make that go away, because we still have to deal with local law 97 in cycle 2035, 2040.
Right. And the usage is going to continue to be reduced.
Right.
The facade is going to continue to age and fail. So
we're looking at options now. Eventually what we're going to have to do with these older buildings is deal with the brick, deal with the veneers, and do something to improve thermal efficiency and reduce air infiltration through these opaque wall areas. And that's where we're presenting owners with cladding options. There's a lot of material options out there. There's rain screens. There's all kinds of things.
metal panels, you could do.
The budget, and they have, we're getting them theoretically beyond. We're getting them to right now to 2035 with the current program that is going to be executed. Phase 2, circa 2030. So now the owner has 14 years to think about. All right. Because you're talking, it's a tough nugget. I mean, $20 million to replace your opaque wall areas. So we've got to start planning that now and budgeting that now. And you touched upon it. We're not going to deep dive in that today, but there are really good financing options out there.
Right, federally funded financing options that are available to help ease the pain a little bit.
Right.
But something that we should touch on just briefly as well is that.
So if we go to the next slide here, I guess we'll sum up the strategy here. And so what we're going to do, we're implementing phase 1 right now. We're going to in 2030, we're going to be dealing with the 10th cycle of FISP. We'll do what we have to do in order to continue to maintain the existing brick masonry veneer. We will be implementing the phase 2 mechanical systems, the energy conservation measures to make sure that we eliminate exposure to local law 97 penalties. And we're developing this long-term plan to get us to 2040 and beyond.
And the program that we have outlined is specific to the case study.
Mm-hmm.
The overall strategy may vary a little bit depending on the building.
There's buildings
because there may be
tackle mechanical first because maybe they don't have terrible FISP issues, right? It's really we prioritize here. I mean, there's sometimes, right, Adam, where the mechanical systems and the operations are so bad that that's kind of the low-hanging fruit, so to speak.
Sure. Right. Or conversely, we may do the facade repairs ahead of the windows. It's a
little bit different. But you got to look at it from our perspective holistically. And we're highlighting the brick masonry facades because the FISP laws have become much more stringent. We have to probe masonry veneer walls.
Right. We didn't even get into the criteria for cycle 9, which include, like you said, John, like probes, verifying wall ties. And as we've experienced, some of the older generation built cavity wall buildings do have an insignificant, insufficient number of wall ties that require supplemental repair.
Well, the nightmare scenario is you open up a circa 1960 wall and you find that the wall ties are simply corroded and snapped. The only thing that's holding the brick masonry in place is gravity and a severely corroded shelf angle. So then you've got a terrible situation where you've got a structurally unstable facade. You have very poorly performing mechanical. I mean, it's a really challenge. And that's why by looking at this together and doing real testing and real analysis, we can come up with a 15, 20 year prioritized phased approach to hopefully, mitigate the exposure to penalties and really phase out the cost.
Right. Keep the public safe, increase the value of your building, the performance of the building, the overall net effect on the world. It's all really positive stuff.
Well, nobody wants to walk into the lobby either and see a sign that says FISP status unsafe and energy status D.
Right. You know, so with these upgrades, right, there's kind of the intangible, right? The return on investment that is not so dollars and cents that we could put in a graph, but upgrading your facade adds curb appeal. It adds market value to your condo or co-op, or you increase rental fees for your, you know, beautifully restored or revamped building that, you know, 5 years ago was, you know, just an eyesore. So there's a tremendous amount of return on the investment in multiple facets with this approach.
And we have partners that we work with in terms of finding out funding sources, sourcing out grants, the PACE financing program. So there's a whole component that could be integrated within this long-term plan of action for compliance that can include the financial assistance, so to speak, and how we can help owners pay for this as well. So
I think we beat this horse pretty good. So yeah, I thank you everybody for bearing with us, and we hope we educated you a little bit today. We have some time left, and we'd love to take some questions if there's anybody out there who has anything specific they would like to ask us. If not, you can reach out to any of us. Oh,
I have no question. I have no questions coming through, but if anybody wants to put one in the chat, please do. I want to let you know that the recording of this seminar, plus a white paper that covers the subject matter, will be available afterwards. If you don't have any questions at the moment, but want to follow up with us, please reach out. You can get us at info@cany.com. Or call the main number, and you can reach John or Thomas, or we'll get you connect with Adam as needed. But here's one question: are there any issues you're seeing with solid brick wall buildings?
Yes, I mean, from a FISP perspective, sure, certainly. I mean, the solid wall is certainly, they're not particularly energy efficient, but you're not going to be demolishing a solid wall brick masonry building. I mean, from the building envelope perspective, aside from that's typically where the fenestration, the window replacement is a key element.
Yeah, roof replacement, window replacement will certainly be the areas that will benefit you as it pertains to Local 97. The good thing about solid brick wall buildings is they're not very energy efficient in mass, but they do lend themselves to good air barriers. So generally you don't have the tremendous amount of air passage through those buildings that you do in a cavity wall construction.
Right.
So and also they fare better over time. So the damage that you see,
they're more stable.
Yeah, and a cavity wall building can often be more catastrophic in failure than a solid brick building. But they need to be looked at. They need to be evaluated. You need to, you know.
I mean, that's where, from Local 97 perspective, outside of window replacement, that's where it's going to be heavy in mechanical. That's where you're going to be looking at building operations, the actual equipment. In some cases where we've white box commercial solid wall office buildings, if they were going to take off interior finishes, we can put an air barrier and insulation
on the interior side. Yeah,
board sides. There's options like that. That's not so easy to do in residential, obviously. Right. You know, so again, that's where it's so important to tie in mechanical and building envelope when you're looking at these two laws.
So another question here. What are the issues with glass wall buildings?
Oh, that's a whole other.
So it depends on the era in which they were built. Modern glass wall buildings are rather efficient and
look, you got the curtain wall buildings that are going today are actually really, really energy efficient. That's the glass design. That's a whole other seminar. But we've got these older curtain walls from the 50s, 60s, 70s, 80s, and into the 90s. That did not utilize, some did not have any thermal break at all in terms of the aluminum structure. The spandrel, the opaque wall areas tended to be a 1/4-inch metal panel.
Right. No insulation, no air moisture barrier.
You know, and a CMU backup wall that looks like the photos we've told you before.
Right. So the back of those buildings often resemble the back of the buildings that we spoke about today.
Right.
Instead of a brick masonry facade, you have a glass structure that's covering.
So what we're doing with a couple of buildings right now, we've got some 1955 era curtain wall buildings. Like I said, they have 1/4-inch glass, non-insulated, 1/4-inch aluminum frames, but the structure's good. And rather than rip the entire wall off the building, we can we have worked with curtain wall manufacturers to develop a cladding system. It's similar to a window replacement in concept, but you can clad those buildings with very high performing, thermally broken, very well insulated panels that would get us to the same local 97 state as we talked about for 2030 and beyond. And again,
And eliminate some of the FISP issues they have with sealant issues and mullion covers and aluminum cladding that gets loose and displaced. And we've done this actually in occupied buildings.
Yes.
Right, fully occupied hospital, and we've reclad the facade while they were doing surgery around the other side of the wall. So very feasible. We have a lot of intimate knowledge with that.
The next, our next webinar would actually focus on these curtain wall, these glass curtain wall buildings, again, from the 1950s all the way up to the 1990s, before they got into the modern thermal break, modern insulated glass technologies. Stay tuned.
Great question. Thank you.
Thank you. Seeing no other questions coming through. So again, if you do have questions you want to follow up, please reach out to us at info@cany.com or call our main number and we'll happily respond. Just to wrap up, I want to thank John, Thomas and Adam for sharing us their insights and conversation. This is a webinar that will be repeating in other guises, as John has indicated. We think there's a whole slew of topics that will benefit from discussion. So please look out for those in the near future. Otherwise, thank you very much for attending and look forward to hearing from you again in the future. Thank you. Bye.